Hello everyone, today we're going to be going over graphing polynomials in standard form. So based off of their standard form equation, there's some pieces of information that we know already, but there's a lot of pieces that we need to figure out, right? If we can get this into a factored form, that would make it a lot easier for graphing, since we've already talked about multiplicities, finding zeros, and behaviors, all that fun stuff. If we can get this into factored form, it would definitely help us out a lot. So let's take a look first. The only piece of information really that we know right now is that our last term here is going to be our y-intercept. So y-intercept is going to be at 0, 30. But aside from that, we need to start using our rational root theorem to try to see if we can find any rational roots for this standard form equation. For rational roots, we're looking at plus or minus. Our constant term at the end is a 30, so it's factors 1, 2, 3 goes in, 4, 5, 6. We got a lot of factors to test out here. 10 is on there, 15 is on there, 30 is on there. That's a lot of factors to test out. Thankfully, it's all over 1, so that's, at least not as bad as it could be. So let's start testing out some factors and let's see what works. Let's see if I test 1. Hopefully that works. -8, -23, and 30. So I'm just doing synthetic division here. Bring down the 1, multiply, add, multiply, add. Oh, look, that one works out for us because we get a remainder of 0. So if we start writing out this function in factored form, it was called f of x. So I know that I can take this root here, translates to a factor of x minus 1. And then this here, as long as I put my variables back in, 1 less degree than what I started with, that's going to give me at least my second factor. From here, I need to see, okay, well, can this be factored anymore? Are there any factors of 30 with a difference of -7? And sure, absolutely there is. So then if we factor that part, that stays the same. If we factor this part, we have an x, a minus 10, and a positive 3 will multiply to -30, but when added together will get us to -7. So we see here that we have 3 roots to our polynomial here. We have an x-intercept at 1, we have an x-intercept at 10, and an x-intercept at -3. The multiplicities of each one of those factors are a 1, so that means we get to cross for every single one of them. Last piece of the puzzle, we're looking at n behaviors. So again, even looking at this factored form here, we're looking at a third degree polynomial with a positive leading coefficient. So that means our n behavior, as x is approaching -infinity, f of x approaches positive infinity. Approaches -infinity. As x is approaching positive infinity, f of x approaches positive infinity as well. So if we're sketching this out, we know that our graph starts in the -infinity direction. That's its left end behavior. The right end behavior, it's ending in the positive direction. And then we just start plotting. So I try to leave you guys with blank grids so that you can set up your own scales. I know I need to get up to a positive 10. So let's see if I count by 2s. So 2, 4, 6, 8, 10. That works. So -2, -4, -6. We get an idea. If we start plotting our zeros, then we got a 0 we set at 1. So I'll approximate that. We have a -3. I'll approximate that. And a 10, approximate that. So following our n behaviors, we knew we're starting out in this negative direction here, and all of them are crosses. So cross, cross, cross. Right. Last piece of the puzzle, we know that our y-intercept is 0, so I'm just going to plot that up there as well and label it as 0, 30. So one example down for graphing polynomials in factored form. Let's take a look at our second example here. So we are looking at an even degree polynomial with a positive leading coefficient. So from an n behaviors perspective, we're going up and up as x is approaching -infinity. f of x approaches positive infinity, as x approaches positive infinity, f of x also approaches positive infinity. If we're talking about y-intercept, we can look at the last term here. So 0, comma, negative 5 is going to be our y-intercept. Clean that up a little bit. All right, and then let's start looking at our rational root theorem. So factors of our constant term are going to be 1 and 5. Factors of our leading coefficient are going to be 1 and 2. So that means I need to test out 1, 1/2, 5, and 5/2, positive and negative versions of both of those. So let's test out 1. So I have a 2, a 3, a negative 3, a 3, a negative 5. Bring down our first term and multiply and add and multiply, add, multiply, add. Oh, it's working out for us. Love it when that happens. All right, so when an x-intercept is going to be 1 here, we know that we could start rewriting our polynomial. This one was f of x. So we have an x minus 1 factor coming from the minus 1 that's here, or a positive 1 that's there. So that root is a factor of x minus 1. And then it looks like we had a 4th degree polynomial here. So as I'm throwing my variables back in, it's going to be 1 less degree than what I started with. So this second factor here, all right. So I have choices. I can do rational root theorem again with this cubic, or it appears that it's factorable as is by a grouping method. So I can actually factor it as is. If I group these two together and then group these two together, the GCF of the first group, it looks like, is an x squared, which would leave me with a 2x plus 5. The GCF of the second set really just looks like a 1, but see that it leaves me again with a 2x plus 5. That's how I know it's factored by grouping, because these middle factors, the 2x plus 5, is the same for both. So that means my f of x equation, I can bring down my x minus 1. That 2x plus 5 that was in common is actually one of my factors. And then what's left over, the x squared plus 1 is the other factor. So let's talk about what our zeros are. This one's easy enough, x equals 1. This 0, keep in mind, some people are still telling me negative 5 for this. No, take a look at it. You have to say each factor equals 0 and solve for x, which means you're going to subtract 5 and then divide by 2. So subtract 5 and then divide by 2. It's negative 5/2 or negative 2.5. For this last factor here, we get a complex conjugate, right? If we go to subtract 1 from both sides of this factor set equal to 0 and go to take the square root, you're going to get positive and negative versions of the square root of negative 1, which we know is a complex number. So x is equal to plus or minus I here. So we have to take a look at the complex conjugate, and we'll sketch that out somewhere in our drawing. So let's start plotting. We know we have x is 1. So I think I could scale my graph probably by 1 now. X is 1. X is going to be negative 2.5. We said that before. Okay. And then we get a complex conjugate in there somewhere. So we know for each one of these factors here, this has a multiplicity of 1. This has a multiplicity of 1. So both of them are going to be crosses. And then we have to just take a look at that complex conjugate and put that somewhere in our graph. So as to the specific whereabouts of it, we've learned in prior videos that we don't know for right now exactly where that is, and we just need to be comfortable with it. We just have to show some place that look of a complex conjugate. And then when you guys go to take higher level math is when you can look more in depth as to where that is. So with that being said, I'm going to choose to draw it on the right-hand side of my graph. So I'm going to go here first. I'm going to cross over. I'm going to cross over this root 2. And then I'm going to make my complex conjugate over here. So Amending positive in both directions. We've talked about that end behavior before. And the fact that we have this little wiggly dip over here is what signifies that we have a pair of complex conjugates. Notice I could have drawn that somewhere over here from the starting point. I could have done a little lip and then brought that down. Totally fine. I could have done something down in the middle here, and I could have changed it over here as well. Any of those are possibilities, but you just have to show it someplace. All right. 3. Let's take a look at some options here. This one, we see that we have a third degree polynomial with a negative leading coefficient. So as far as our end behaviors are concerned, as x approaches negative infinity, f of x, it's got opposite end behavior, so it's going to start out positive. As x approaches positive infinity, f of x is going to approach negative infinity. So it's going to start up here, and it's going to end somewhere down here. All right. So from here, let's take a look. We know we have 16 as our y-intercept. Okay, so that gives us some idea. And then let's start listing out our rational root theorem. So we have factors of 16 are 1, 2, 4, 8, 16. Factors of our leading coefficient are 1 and 3. And then we have to start testing them out. So I already know 1 and negative 1 does not work. If we look at 2, let's start setting it up. 20, negative 36, 16. All right, so negative 3, negative 6, 14. So that's 28. When I subtract that, I'm going to get 8 times, negative 8. So that's negative 16. So that is a 0. Beautiful. So start writing out the factors. I got x minus 2. And then I get negative 3x plus 14x. Oops, what's x squared? Because I'm looking at a third degree. Yep, perfect. And then from here, we want to see if we can factor it. I generally preferred that I factor with a leading coefficient that's positive. So actually right from here, I'm going to pull a negative out front, and then I'm just going to change my sign. So that's going to be positive. This one's going to be negative, and then this one's going to be positive. I just like it that way. If you're fine factoring with a negative, go ahead and leave it in there. Totally fine. From here, I want to factor. So the factors of 24 that add up to 14. So factors of 24, if you're a visual person, you probably want to list them out. 1 and 24, 2 is 12. Oh, right there. Nice and easy. That's going to give me 14 for sure. So let's go ahead and factor. So if I factor this, if I use bottoms up, I get x minus 12, x minus 2. My leading coefficient is a 3. So that means 12 divided by 3 is going to give us 4. So that means that's x minus 4. And then this bottom here, I'm going to bring that up. So here are my factors. So looks like here I get a 0 at, or an x-intercept at 2. I get an x-intercept at 4 and an x-intercept. Remember, this is not 2, right? We have to add 2, but then divide by 3. So 2, 4, and 2/3. So it looks like I can count by 1 again. Here's 2, here's 4, 2/3 is going to be back there. From the multiplicities, they're all 1s, each one of those factors, so that's going to be a cross. I know my y-intercept is going to be at a positive 16, so I'm going to put that up here, 0, 16. So I'm going to start out in this positive direction, make sure I go through my y-intercept, go down to 2/3, cross, 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 into that negative direction. Okay. Last one, example number 4. Positive leading coefficient here, third degree polynomial. So end behavior as x approaches negative infinity, f of x will also be approaching negative infinity. As x approaches positive infinity, f of x approaches positive infinity. All right, let's take a look. We got our y-intercept. We know that at -4. Right? And let's start listing out our rational root theorems. So factors of 4 are 1, 2, and 4. Factors of our leading coefficient are 1 and 2. So if we start testing out the possibilities, I believe 1 is going to work. So let's start there. -2, -4. Yes, it's trial and error, but I've done these out before. So just for the essence of time, I skip over the ones I know don't work. 2 and 6 and 6 and 4 and 4 and 0. Beautiful. So start writing out the function in factored form. So x minus 1, 2x squared plus 6x plus 4. Well, we know if nothing else that we have a GCF definitely of 2 in our last factor here. So I'm going to go ahead and pull that out front. And then I'm going to look to factor this trinomial some more. So are there factors of 2 that add up to 3? You know there are. So if I factor this, I'm going to get x plus 2 and then x plus 1. So if I'm looking at my roots, I have a root at +1. I have a root at -2 and at -1. Again, all of those have a multiplicity of 1. So again, they're all going to be crosses. So let's pull out our -2. I'm actually going to space this out. I'm going to make that -1. I'm going to make that -2. So because I'm making it something other than a scale of 1, I need to make sure that I label it. And then +1 then is going to be over here. That end behavior we spoke about before. I'm starting out in this direction, right, and ending positive. Each one of my multiplicities, again, were a 1, so I'm going to cross at each one. So I'm starting out, whoops, that's not my draw tool. Try that again. All right, starting on the negative direction, and I'm going to cross, cross, cross. Perfect. And then make sure I'm labeling my y-intercept. And we are done. We just graphed 4 functions in standard form. Pat yourself on the back. That was a lot of work. Good job.